The locating industry the way it is now, it seems to me that one of the most important things is actually the infrastructure knowledge.
So we're building a new generation of utility locators and transmitters that are going to be geo-aware.
Our business has been completely focused. When you're running a business, I think you want to try to be the best of the world at something.
SeeScan is an engineering manufacturing company, so we make two lines of products, pipe inspection cameras and utility locators. So on the utility location side of the business, that's where SubView fits in, and it's a companion tool to go with our new generation of locators. And it is to consume data from them and automatically create maps of what's under the ground.
I work with a team of algorithm engineers here at SeeScan. What we do is basically handle all the math and science that goes into making our products work. So that includes a lot of different things, including electromagnetic processing GPS signals, processing inertial data, magnetic data.
I mean, everybody here has a role to play. So there are people doing all sorts of different tasks. Product development process is long, and it starts with an idea and it grows into a product, and there's a lot of steps, and it's not necessarily a linear process from one to the next. There's a lot of places where you build something and it's not quite right, and you revert back to the previous step and you go again and you keep going until you get it right. What I do is that, I do spend a lot of time walking around and asking questions, trying to keep track of what's important, trying to go and gather information, and I really like to gather the information firsthand. I'll send a fair number of emails, but I like to show up in person and get a sense for what's really going on. People maybe in one office may be working on SubView, in the office next door they may be working on a sewer inspection monitor. Mostly people have different skill sets and they have different talents, and we try and bring them to bear on the problems where they're most applicable. So people can switch back and forth between the things that they're working on.
I'm a big believer that strength and diversity. If you're trying to build a culture of innovation, innovation in some sense is about having a lot of different ways of looking at problems, and having people with a lot of different life experiences, a lot of different cultural backgrounds, so long as you can get this group of people to intermesh and play well together, basically, in a respectful space. I really do believe that there is enormous strength in diversity. And we, some years ago, decided that one of the organizational core competencies that was really important to work on is finding and recruiting good people.
When we're looking for people to hire here, there's lots of people that have a lot of intelligence, a lot of people with a lot of skills, but the most important thing is finding people that fit with us and our culture. We have a really specific culture that's really based on the spirit of innovation and the common core values that we all believe in. Really, it's important for people to feel passionate and engaged in what we're doing here, whether it be pipe inspection or damage prevention or whatever other thing we're working on. Having a passion for getting that thing done is really important.
I've spent a lot of time talking with these customers, and I go out and I travel and I meet with them and I interact with them. So I get to bring that back, and I bring all that experience back to the people who are creating the products to make sure that they understand from that customer point of view what it is that they really want and what they really need, and to make sure we're making those products to solve their problems and to meet their needs.
Our goal is to map underground utility infrastructure. So basically be like Google Maps, but for pipes. So we want to have a web portal that people can go to, and they can view maps of what has been discovered under the ground using our systems.
Grew up in Arizona, the Phoenix area. In 1968, my father worked for Motorola, and he was offered an opportunity to move to Guadalajara, Mexico. And I thought, well, that's cool. That sounds like an adventure. I always like sort of new experiences and novelty-seeking behavior, I suppose. But so December 1968, we got in the car without speaking a word of Spanish and drove down to Guadalajara. I built a dark room at the high school and ended up being the yearbook photographer for the American School of Guadalajara for 2 years. And then we moved from Guadalajara to the San Francisco Bay Area in 1972. I went 1 semester in the high school system in California, which let me get residency, so I could enroll in the California universities cheap. Back then it was way cheap. It was $212 a quarter. Total fees, it was like, what a trip. I showed up in 1973 at UCSD and started in Revelle College working on a science degree. And then I got involved in scuba diving, and I was combining the photography. I decided to build my own underwater camera housing. I did a Canon A1 and built a whole housing from scratch. My first instrument went to the bottom of the Marianas Trench, recording sound in the bottom of the Marianas Trench, and then I moved on to building probably the very first VHS deep sea recording system on planet Earth. It went 20,000 feet into the North Pacific. You build something called a free vehicle that sinks down to the bottom of the ocean. It turns the camera on the timer, records images of deep sea animals doing things like coming to bait, and then it drops the weight after a certain time, floats back to the surface, and the ship recovers it. You develop the film, or you play back the videotape. We did film first, and then videotape later. Started a company, we came up with deep sea power and light, and we made an underwater battery, and I figured we would get into lighting at some point and probably imaging later. So our first product in 1983, we started in a garage in a rental house here in San Diego. And then around 91, 2 different things happened. Somebody in town knew we made underwater cameras, and we had taken a small camera and put some little tiny lights on the front of it. I had a friend who had a company called Underwater Kinetics who made diver flashlights and made these little tiny light bulbs. So we took some of his light bulbs and put them in little tiny reflectors and put them on the front of the camera. And for somehow, some of these guys in Idaho, I don't even remember their names, found out about us and purchased one of these cameras. They started putting them in the sewer pipes. And then a company called Drain Patrol in town asked us to build them some pipe inspection cameras. So we made 10 cameras that we called the Drain Cam. This is probably in 1991. And we learned that plumbers are really good at destroying things. It's a very violent, the whole thing is, how do you make something that a plumber won't break? Because they just want to use it as a tool. Right around 1990, 91, 92, the red LEDs started getting efficient enough, and the CMOS cameras came along. Sony started making these little solid state cameras, and they were a lot more suitable for the underwater world. So we were kind of at the right place at the right time. One of my favorite sayings is, it's great to be smart, but it's even better to be lucky. As soon as we started shipping cameras, it became apparent that people wanted to use these things called locators that I'd never heard of to find out where their cameras were. Where's my camera? How deep is it? The first instrument we made was a locator called Navitrack, the first Navitrack, and it had a lower node and an upper node. And then we made another instrument after that called the Navitrack 2. One of the things we did was we put a folding joint in the thing. One of the advantages of using these what call air coil antennas is they can operate at a lot of different frequencies. They're broadband coils. So we immediately jumped into a broader range of frequencies because we had an antenna technology that would allow us to do that. It's not because we were smart, it's just because we could. So it's like, well, if we could, maybe it would be interesting. We should try that. Let's try to make the locator that will do everything. One of the things I noticed is the way locators are fundamentally used is you wave this instrument around and the human interprets the sound and the signals and the numbers from the instrument, and then the human synthesizes that information and decides that utility is here, and they get out the spray paint and they put the mark on the ground here. Having tested and walked a lot of miles of locators, it becomes very obvious that the paint's obviously in the wrong place a lot of the time. Even on critical, like 16-inch high pressure gas lines and things, it's not always in the right place. So that's the problem with locating, is you're trying to locate something that's completely invisible that no one can see, and you're trying to transform that information into something that someone can make sense of. I want to know whether I'm on top of the line, and I want to know how deep the line is, and I want to know, if I can, what kind of utility it is, and I want to know to what degree should I be confident that it really is there. That's what I want to know. I don't want to know what frequency to send my transmitter to. This is a waste of everybody's time. You just want to know where that utility is. My fundamental premise is the instrument has to know where the utilities are. It must not depend on the human that is using the instrument to know where the utilities are. The data that the instrument collects must know where the utilities are. We started using the word mapping, and the idea is, I think we can make a mapping locator.
It's pretty apparent that people are interested in mapping underground utilities. There's a lot of discussion about, why are there not maps? Why can't we get maps? How do we make good maps? Why are we not at least mapping things that we're putting into the ground now?
The thought process is if you're going to go to the trouble to go out and put your life on the line locating an intersection, or you're going to go to this trouble to go out into the field and collect data, why not try to locate everything that you can possibly locate while you're at it? Because the human and the effort and the time and the expense of putting a person out there doing the work, why not leverage their time with really better technology? How much blood can we squeeze out of this technology turnip to leverage that person's time to the maximum degree possible? What can we do to make that happen? So we started looking at multi-frequency induction, multi-frequency active transmitters, massive multi-frequency passive locating. And then we thought, well, maybe we could make multiple channels. So what if we could hook up more than one transmitter at the same time? So if you want to go out and if your job is to locate everything in the intersection, because that's really the problem, okay? If you're the guy that's the excavator that's come along and you're going to dig a trench through that intersection to put in a new power line, to put in a new 5G fiber, to put in a new gas line, to rehabilitate the sewer, what you care about is you need to know where everything is. You really need to know. It's not like just knowing where the water is. And you really, really, really need to know where everything is.
You hear that customers are asking for any tools they can have that can help them know where the utilities are. Any tool they can have in their toolbox is one more tool that's a step closer to preventing a damage. And the technology that we've been working on for many years is a technologically advanced tool that the market has never seen before.
Our number one priority is to kind of finish developing and bring to market our geolocating system. SubView is a component of that system. SubView is the online cloud-based backend to the geolocating receiver and transmitter combination.
Geo-aware locators are, you can imagine your typical existing locator, but it has GPS antennas on it, and it has orientation sensors so that we can work out where it is in the world and the orientation that it's at in the world. So is it facing north? Has it been tilted? And so from that information, if we know that a utility is, half a meter to the left and 1 meter in front of the device, but the device is upside down, then we can still resolve that and work out what that means in terms of, north, south, east, and west, and latitude and longitude of the utility that we're detecting.
One of the things that's special about our system is that we have a computerized system for figuring out where the utilities are. Most of the systems that are out there are systems for letting the user indicate where the utilities are. So we're actually taking the electromagnetic field and we're inferring the utility positions directly.
My vision of this mapping problem is you ought to be able to go out and do what would be really a typical normal locate for the most part, and you just get a map. All you have to do is get signal on the utility, walk over the utility, walk over locating, and the recorded data from the instrument should be able to provide an accurate map of the depth, position, orientation of the utilities in the ground.
There's sort of like two parts to this, and one is what happens on the locator, and the other is what happens on our web tool. And the way it works is when it's on the locator, you want to be able to just turn the thing on and see the utilities and know exactly where they are without having to think at all. You just look at it and you know exactly what's going on. It's the same thing, but in a different form for what goes into our web tool. So there, you get to see all the utilities exactly where they are, exactly with what they're in relationship to in the real world.
As part of SubView, we're also incorporating other data sets that might be available. We're working on experimenting with having drone operators collecting high-resolution imagery of areas and using that in conjunction with our utility locator data. So then we can plot the utility maps that we're collecting on top of schematics that might be available, any other data sources we might have, and on top of really high-resolution base maps.
As you're driving, if you're hooking this up to a hitch and you're driving along with the system and this data is going to go up to SubView, you can cover a huge area in a small span of time and be able to pick up everything that's around you in just one go and be able to put it all on the map and see everything at once without having to go and hook up everything individually and locating each utility on its own, or even knowing necessarily what you're looking for. It'll show you things that you weren't even looking for that you can then go back and say, oh, it looked like there was something right there. I want to see what is there that's actually there and locate that further and find out exactly what's there, whether it's an abandoned utility or something of interest that you just hadn't seen to pick up on.
I wanted to build a locator that would find that other stuff even though they didn't have an active transmitter. So we started focusing on the passive locating problem. Passive locating problem is signals of opportunity, okay? What is there if you don't have a transmitter hooked up? The more information you have about a problem, the better you can probably solve the problem. And locating is a really hard problem, okay? You have multiple utilities in the ground, you have multiple distortions, you have multiple uncertainties. It's dry one day, it rains the next day, everything changes. The conductivity of the ground changes. You have a lot of uncertainties, you have grounding issues, everything's connected to everything. If this is not like there's a wire in the ground that's not connected to anything and you hook a transmitter to it and it's ground the other end. This is not reality. This is not what the world looks like. It is wicked complicated.
So what we're doing is we're capturing the roadway using drone technology, and what we're doing, we're taking the lens, pull it straight down. We're capturing a nadir shot of the roadway, and we're going to take those photos and turn it into an orthomosaic image. And then with that image, we'll be able to use our data to be able to detect where that utility is located underground along that roadway. And again, using drone technology, the quality of that imagery, seeing that on a map, and also seeing that utility where it's located on that roadway will be amazing to see. Everyone's familiar with looking at Google Maps to navigate to where they're going. And imagine that you're able to see utility data laid on a map. Imagine seeing it from macro down to drone imagery, down to where that utility is located, macro to micro. And we're taking snapshots of that utility, that area of interest. And then we take those snapshots and we stitch it together into an image, an orthomosaic. We use the latest drone mapping software to help stitch that imagery together. We take ground control points to make them survey grade imagery, and then we put that into our SubView system.
So last night we drove from here into La Jolla, about 25-30 minute drive, and along the way we decided to do some locating because I wanted to give you the sense of what the system could actually do. And so we have a pair of these hand carry locators on the rear hitch. We have a pair of high resolution GPS units, and we're recording data as we drive. Drove into the parking lot here and started logging, and then drove the car, and we drove along this 69 kV line. The 69 kV line comes down here, goes out into the middle of the lane across here, and I have this map many times, and it goes diagonally across here and comes down and then goes into the substation here. And I wanted, for example, to map this one little section just to sort of show an example of what this thing could do. Within this session, we have some data information. And this particular session, the whole recording session, it took us 1 minute and 52 seconds, and that was starting the logging, getting back in the car, driving around the loop, stopping the car, getting back out. This entire data collect to map these utilities was 1 minute and 52 seconds. This data is being plotted from 0 to 3 meters deep, which is about 10 feet deep. The minus 3 meters, which is negative going down, is black, and shallow at the surface is red. These are crossing utilities. I would say we could go out and hook up to this light pole here, and actively there's a street light right here, and I'm pretty sure this is a parking light feed that probably comes over from one of the light poles over here someplace and comes across. Here's some of the traffic loops. This is very shallow. This is red because it's essentially just a couple inches below the surface of the asphalt where they put these loops in. This is, again, passive locating. If we kind of look at this, where the car is accelerating considerably, so we're already up to 13 meters per second speed, which is probably about 35 miles an hour at this point. So we're instantaneously locating this fiber at 35 mile an hour velocity. I'm going to go ahead and turn these path plots back off so we can just look at the utility data underground. This thing comes up. It's clear that the utility is turning and going off to the side here. There's another utility across here. It could be the same one. We've done a number of intersection scans, okay? And if you pick an intersection like this and you just drive all the different lanes and find some early morning, you essentially get a snapshot of pretty much all the locatable utilities in the intersection in about 50 minutes. You can't have everything on 50 different maps, okay? It becomes incoherent, the maps are on different scales. You need to put all the available best information you have into a single frame, a single context. But the good news is I think everything can be remapped over a reasonable period of time. And as you expose, if we can get people, as they're doing installations, to also map during the installation and make that really easy to do, which is just like locating. You use the same process you use to locate, you use to map an open trench, and you just do everything that way, then I think there's a big win.
We pride ourselves on making the highest quality tools available on the market. And we've been telling the market for a long time that we're gonna have this tool any day now, but we don't stop until we have the best tool that we can. And one of the reasons it's taken us so long to get here is because it's not good enough for us yet.
Geolocating, it's kind of gonna be the way of the future. This is not your grandmother's way of locating. As soon as you pick up the device and you start walking around with it, you feel that I can tell exactly where that thing is, because as I move around, I see that reacting exactly the way I expect it to. When you combine that with our mapping technology, it just opens up this whole new world of being able to view the universe of utilities in a way that we've never been able to before.
So I do think the industry is getting better, and we're having more things like the roundtable where conversations are happening and people are getting together and discussing ways that things should be changing, and that's a precursor to actually changing.
There's one saying is most great things are created for their own sake. And when I think about myself, I think I'm sort of internally driven I'm a builder. I like building and creating things. So from a selfish personal satisfaction point of view, it's really fun to build and create things. I used to tell people that when I started out, I wanted to build the world's best underwater light. And that probably was true for the first 15 years of doing either the best underwater camera or the best SeeScan. And I got to a kind of a transition point where it became more interesting to build the thing that builds the things. It's all these different pieces. It's building products, it's making plastic parts, it's making this whole system of pieces that will solve this mapping locating problem.